let's talk about cut vertex and cut edge. Okay, so in a graph G, cut vertex is a vertex whose removal either disconnects the connected graph or increases the number of connected components. Okay, so that means if you remove that vertex, either already connected graph should be disconnected or the number of connected components in it should be increased. We'll see one example. I have a graph like this 1, 2, 3, 4, and first I explain you what is the removal of a vertex. Okay, so this is your graph G, and removal of a vertex is an operation. Example, if I remove a vertex 1, what should I do? When you remove vertex 1, remove it and all its corresponding edges. That means this one and this one. Then whatever the resultant graph you get, that is called operation. Here, if I remove this vertex 1, then what happens? You end up with 2, 3, 4, and 2 to 3 edge should retain, 3 to 4 should retain, and 1 comma 2, 1 comma 4 should go, since we are removing 1. So finally, removal of a vertex 1 is nothing but remove its vertex 1 and all its corresponding edges. So simple, isn't it so? Now, this is a vertex removal operation. When I do that, then if it is really cut vertex, what happens is either it disconnects the connected graph or improves or increases the number of connected components. For example, in this problem, number of connected components were 1, isn't it? Now if I remove vertex 1, again number of connected components are 1, right? They are not increased. Then what about the second case? Either number of connected components should increase, otherwise graph should be disconnected. So this is a connected graph. Previous one was also connected graph, right? So there is no disconnection. That means this is not a cut vertex. Okay, I'll give you one more example. 1 to 2, let's take 2 to 3, 3 to 4. Okay, so in this problem, we'll see is there any cut vertex. This one. Vertex 1, is it cut vertex? Let's remove and check. If you remove vertex 1, then you get a resultant graph, 2 to 3, 2 to 4, 4 to 3, isn't it? Yes, connected graph is not disconnected, number of connected components are not increased. That's why vertex 1 is not cut vertex. Let's try 2. If I remove 2, then the remaining vertices are 1, 4, 3, and retain all the corresponding edges of 1, 4, 3, that is 4, 3, that's it. Now if you see, this is a disconnected graph, isn't it? Because there is no path from 1 to 3, there is no path from 1 to 4. That's why this graph was connected become disconnected. So then definitely this vertex 2 is behaving like cut vertex. Okay. So in this problem, I can see only one cut vertex. Try to remove 3, you understand that nothing will happen. That means, so number of connected components will not be increased, and second one, graph will not be disconnected. You see. Example, if I remove 3, then what happens? 1, 2, 4, 3. Okay, I'll show you here. If I remove 3 and all its corresponding edges, still graph is connected. It was connected and now it is connected. That's why 3 is not cut vertex. In that way, you can understand cut vertex. Let's go to cut edge. What is cut edge is? It's an edge whose removal either disconnects the connected graph or increases the number of connected components. What's the difference between cut vertex and cut edge? Cut vertex is about removal of a vertex. Cut edge is about removal of an edge. Then everything is same. Okay. The property of that cut vertex and cut edge is what? Their removal should do the same, right? And you know what is that? Example. Before going to cut edge, you should know what's the meaning of removal of an edge. Okay. So let's take one example and see what is the removal of edge. Example, this graph. Let's take edge 1, edge 2, edge 3, edge 4, edge 5. Okay. So let me show you removal of E1. If I remove E1, then the resultant thing is graph, and that graph is nothing but entire old graph minus just this edge. When we remove an edge, simply we discard that edge, but we don't remove any vertex which is corresponding to E1. Then what happens is here A, B, D, C, right? Just we are losing this relationship between A, B, that's it. Now everything is same, AC, CD, BD. This is called removal of an edge from a graph. Okay. So when you remove an edge from a graph, then the resultant thing also a graph. Okay, it's a graph operation. Now, if you focus on E1, initially it was connected graph, still after removal still it is connected. So that means graph is not disconnected. At least the number of connected components are also not increased, isn't it? So number of connected components were 1 and now also 1. That means there is no increment in number of connected components. That's why I can say that this is not a cut edge. Okay. So one more example we'll see. So let's try to remove E4. Okay. If I remove E4, what happens? Then you get AB, BD and AC and CD. Again same thing, graph is not disconnected, number of connected components are not increased, then E4 also not a cut edge. So whatever you remove here, so graph will not be disconnected. So that's why I can say that nothing is cut edge here. Okay, there is no cut edge in this graph. Let's take one more example. A to B, B to C, C to D. Let's take this one, C to D and D to E. Let's try to find out cut edges in this graph. So what I do is I remove AB and I'll observe A, B, D, C, E. I am removing AB edge, then remaining edges are BD, DE, CD, BC. So this is a resultant graph. In this resultant graph, you can see that connected graph is disconnected. That's why I can say this edge A to B is cut edge. Understand? Similarly, you can realize that D to E also cut edge. Okay, let me draw AB here. If you remove DE, still graph will be disconnected. That's why DE is also a cut edge. There are two cut edges, right? So why this BC, CD, BD are not cut edges? I will tell you. Whenever an edge is on cycle, what happens is, let's imagine one cycle. Okay. Example, there are a lot of vertices which are on cycle. Okay, example 1 2 3 4 5 6 so on. If you remove any edge on cycle, what happens is still all that vertices will have an alternative path. That means this removal of edge can disturb only the path from 1 to 2, correct? So remaining paths are still remain same. Then only thing we have to prove that there is a path between 1 to 2. Yes, there is a path from 1 to 2 in reverse direction, otherwise in anti-clockwise. So whenever there is a cycle, if you remove any edge, then that can at most disconnect two vertices 1 comma 2, correct? Maybe so at least it can disconnect 1 and 2. In this problem you can see that only 1 comma 2 might be disconnected. Since it's a cycle, there will be an alternative direction. If you go through that, still you can reach 2 from 1 or from 1 from 2. So what I want to say is, that's why this edge cannot disconnect the graph. Understand? So when a edge cannot disconnect on the graph, definitely it will be on the cycle. That's why no edge which is a bridge, like otherwise no cut edge will be on the cycle. Whenever an edge is on the cycle, its removal cannot disconnect the graph, because you will have alternative path between every two vertices on that cycle. Okay, so that's why blindly remember from now onwards, cut edge cannot be on cycle. Second one, if any edges are not on cycle, example some edge is not forming cycle, then if you remove it, let's say whatever the remaining graph, example this is a edge which is not on cycle, if you remove it, then that means what? Between A to B there is no alternative path. If there is an alternative path, you would have formed cycle. If there is no cycle, then definitely there is no alternative path between A to B. There was only one path and you disconnected it, then graph will be disconnected. That's why whenever an edge is not on cycle, that edge, between that ends of that edge, like A comma B, will have only exactly one path. That if you remove, graph will be disconnected. That's why that edge will behave like cut edge. Understand? Two important points now. One is, whenever an edge is not on cycle, it is cut edge. Whenever an edge is on cycle, definitely it will be, definitely it will not be a cut edge. So simple. This is a story about cut vertex and cut edge. Now we'll go to the next concept, cut vertex set. What is cut vertex set is, it's a set of vertices, okay, whose removal We'll do the same logic or same concept. That means what? So here rather than one vertex, we are removing set of vertices. So whose removal either disconnects the connected graph or increases the number of connected components. Such combination is called cut vertex set. An example is A, B, C, D, E, F. Let's take this example. So I'm calculating cut vertex set. Its property, the removal of that combination of vertices should disconnect this connected graph. Okay. Otherwise, number of connected components should be increased. Okay. Since it is connected graph, if you disconnect, that's fine. If I remove B, then I think it cannot disconnect the graph. So I need a combination of more than one vertex. Let's try BC. So that is what my idea. If I remove BC, then probably AD will be separated from EF, isn't it? That's why. So I remove now a combination of B comma C. So what happens is you get AD and EF. Since other vertices are removed, then AD EF, right? Yes, graph is disconnected. Connected become disconnected. It satisfies the condition. So this is a cut vertex set. What about B, C and one more vertex? Let me add one more vertex E. Is it cut vertex set? If you want to know, remove that BCE. Then remaining vertices are A comma D. If I remove BCE, you get F. So between AD you add an edge. That's it. Okay. Still F is not reachable from AD. So that's why this BCE combination is a cut vertex set. Okay. So some students argue that BC is cut vertex but not BCE. Then I ask them why. Then they say, sir, there are three vertices. In my definition, I never said your cut vertex set should be minimum size, isn't it? It can have any number of vertices, but property is the resultant graph should be either disconnected or number of connected components should be increased. Okay, so that's why BCE is a cut vertex. Now one more example. What about BCE comma F? Is it a cut vertex? If you want to know, then remove all that vertices at a time and check the resultant graph. The resultant graph is A. So if I remove BCEF, you get AD and edge like this. Graph is disconnected first, and after removal also it is disconnected. Then there is no change. At least number of connected components are increased? No. That means, so that combination BCEF is not cut vertex set. In that way easily we can find out. Okay. Now we'll see the next concept, that is cut edge set. What is cut edge set is, it's set of edges this time, like cut vertex set of edges whose removal either disconnects the connected graph or the number of components should be increased. So concept is same, but here cut edge set is a set of edges. Okay, so let's take same example and we'll try to find out cut edge set for this problem. Let's try. We know that there is no single edge, right? Like we can't remove single edge and we can't disconnect the graph. Let's try two edges. So just try AB and AD. What happens is this A will be isolated from others. Let's try. I am removing AB edge comma. So this is cut edge set AB comma AD. If I do that, the resultant graph is AD. When I remove edges, vertices will not be changed, isn't it? So that's why the number of vertices are same. CD here, CF here, EF here, and EB here. Anything else? BC, right? And this vertex A is now separated from other vertices. That's why now graph is disconnected. Enough to say that this is cut edge set. There is one more reason. The number of connected components also increased. So for any reason I can say that this combination is cut edge set. Okay. So one more cut edge set. Let's add anything for this ABAD. What happens if I add one more thing like EF? So what happens is, already your graph is disconnected. If you remove one more edge like EF, then the graph will be more disconnected, correct or not? So that's why the number of connected components will be probably either increased by some more, otherwise it remains same. So what I want to say is, when you have already cut edge set, if I add one more edge to that, then what happens? This combination already disconnects the graph, and if you remove one more edge, then your graph will be more disconnected. So the resultant set again, will become cut edge set. Understand? So if something is cut edge set, then adding something to that will give you again a cut edge set. That is what I wanted to say. Understand? But that is not the case with cut vertex set. Why? Because for cut vertex set, if you add some more vertex, probably because of that connected components will not be increased, otherwise graph will become suddenly connected. Example I will tell you. It's better to understand it with example. So already we have seen example, b comma c is cut vertex set, isn't it? Yes. So if you remove this bc, you get ad and ef, correct? Now what you do is, if I add e comma f to it, okay, then few more vertices to cut vertex set, then these vertices will be gone, then the resultant component is now connected, isn't it? So connected, then BCEF combination is not cut vertex set, but BC was cut vertex set. So what I want to say is, for cut vertex set, if you add some more vertices, the resultant set may not be cut vertex set, but for cut edge set, if you add any number of edges, so resultant sets will become cut edge sets. That's the difference between cut vertex set and cut edge set. Okay. Now, one important property of cut edge set I will tell you. That is, there is a relation between cut edge set and minimum degree of a graph. How? We'll see. Example, you have a graph like this: A, B, C, D. Uh, let's say this is minimum degree vertex, isn't it? This is a graph. So what is its minimum degree? 1, right? Because it's 1, 3, 2, 2. What I want to say is, if a graph has minimum degree, go to that vertex and remove all its corresponding edges. Then definitely that vertex, that means you are removing that vertex, all the connections, right? That means, example, it's, if you remove all its edges, then that vertex will be separated from others. Then you are disconnecting the graph. That means any graph, if you go to that minimum degree vertex and if you remove all the connections, otherwise edges of that, then how many edges you will be removing? Exactly equal to minimum degree. Then are you not disconnecting the graph? Yes. So the summary is, any graphs, cut edge set size, definitely, that means minimum number of edges required, I can say, to disconnect the graph is not more than minimum degree. Example, let's say this is your abstract graph. What I want to convey is, its minimum degree is 10. That means other degrees are 11, 12, maybe 10, 13, okay, not less than 10. Then its minimum number of edges, the question is minimum number of edges required to disconnect this graph. Okay, so this is what I am going to discuss. Since I don't know the structure of the graph, still I can get some points about this graph. That is, minimum number of edges required to disconnect this graph is, I don't know exact answer, but it is not more than 10. Okay, why? Because I will go to minimum degree vertex. Example, that is vertex u, its degree 10, right? So minimum degree, I disconnect all its corresponding edges, then definitely graph, this, if it is already connected graph will be disconnected. If it is already disconnected graph, then because of this new removal, then number of connected components will be increased, isn't it? Because you are, for already disconnected graph, you are disconnecting it more, then number of connected components will be increased. Example, you see A, B, C, D. Okay, let's take one more component, E, F, G, H. Like, see, what is minimum degree? 2, right? For this graph, go to this vertex A and target it and remove all its edges. Then this component will be disconnected. Initially the number of components were 2, Then if you remove these edges, this vertex edges, then the number of connected components will become 1 plus this connected component will become 2. Then it will become 1 plus this is 2. This entire thing is 3. You understand? That means I can disconnect the graph, in a better way. Otherwise, I can increase the number of connected components. So what I want to finally convey is, so by removing all that, minimum degree number of edges from the graph, I can disconnect any graph. Understand? So the method also very simple. Go to that corresponding minimum degree vertex, remove all that corresponding edges. Then graph will be disconnected. Correct? Otherwise, number of connected components will be increased if it's already disconnected graph. Then minimum number of edges required to disconnect this graph cannot be more than 10, because I can do with 10, right? Just now I taught you that with 10 edges, removal of 10 edges will, do this work, cut edge set work. Then minimum number of edges required to disconnect any graph is not more than 10 for this graph especially, correct? So anybody if says that minimum number of edges required to disconnect this graph is 12, then I argue that it is wrong. Why not it is 12? Because I can do with 10, right? So that's why there is a, relation between minimum number of edges required to disconnect any graph with minimum degree. Example, minimum degree of your graph is delta of g. Okay, then the question is minimum number of edges required to disconnect any graph is, let's say, lambda. Let me denote it by lambda. What is lambda? Minimum number of edges required to disconnect a graph, lambda. Then that lambda is not more than delta of g, because I can do with delta g. Then lambda is always less than or equal to delta of g. This is one important point you should remember. Okay, what's the relation between lambda and delta of g? Lambda cannot be always less than or equal to delta of g. So why less than or equal to, why not equal? I will tell you. So it is not compulsory to remove lambda number of, delta of g number of edges. I will show one more picture. Some students don't understand, this equation properly. So they think that, lambda, that means minimum number of edges required to disconnect the graph, they think, it is equal to delta of g. But it's wrong. It is either equal to delta of g, sometimes it may be less than that. Why? I will tell you. So example, you have a graph like this, A, B, C. Let's connect it with single line like this, then D, E, F. Okay. So it is sufficient to remove, delta of g number of edges to disconnect the graph, but it is not necessary. Example, in this graph, let me add one more edge here. So what is minimum degree of this graph? If you see, 2 and 2, 3, 3, 2, 2, right? So minimum degree is 2. So by removing two edges, I can disconnect this graph. Example like this one and this one, but it is not compulsory, right? So by removing single edge like this, still I can separate this entire component from this one. So that's fine, but not more than, you never need more than two edges, to disconnect the graph. So that's why minimum number will be, so it is either 2 or maybe less than that. Example, less than that here. So one edge is sometimes sufficient. Okay, depends on the graph structure. That's why. So in this graph, let's observe the values. Minimum degree is 2, right? And minimum number of edges required to disconnect this graph, let's say denote it by lambda, that is 1, right? One edge is enough to disconnect it. So that is minimum. So see the relation, they are not equal, but definitely this lambda is either equal to or less than delta of g. That is what, I wanted to say, you see. So lambda less than or equal to delta of g. Understand my point? Okay. Now let's see two more concepts in this cut vertex concept, that is vertex connectivity number. Usually this is denoted by K. Second one, edge connectivity number. Okay, edge connectivity number, usually it is denoted by lambda. So already I discussed, about lambda, but I will discuss now what is K. Okay, so vertex connectivity number is easy. It is minimum number of vertices required to disconnect the connected graph, or otherwise to increase the number of connected components. That means I can say that the vertices whatever you remove, that should be minimum, and they should have vertex set property, cut vertex set. Okay, it's I can say that vertex connectivity number can be defined as cut vertex set whose size is minimum, right? So I can say that it's a size of cut vertex set. Which size of cut vertex set? Whose size is minimum. Let me write like this. Answer is it's cut vertex set size whose size is minimum. Understand? That means what? So it is minimum size cut vertex set's size. Okay. Now similarly I can define edge connectivity number, that is minimum number of edges required to disconnect the graph. Okay, so generally, so to disconnect the graph we use cut edge set, correct or not? Then what is the relationship between this cut edge set and edge connectivity number? Edge connectivity number is, let's say, lambda is nothing but its size of the cut edge set, but which kind of cut edge set? Whose size is minimum. Whose size is minimum. That is the definition of edge connectivity number. Okay, so let's recall these two things again. This is K. In set theory we write this kind of definitions. Okay, that is K is a number. What is that number? Mod of cut vertex set. So what is cut vertex set? Whose removal disconnects the connected graph and so on, right? And but any cut vertex set size? No. Whose size is minimum? So we have to pick a cut vertex set whose size is minimum. That's why here we have written a condition. Okay. So finally K is a number. It is nothing but size of the cut vertex set. So why are you saying that it is number? Because mod of cut vertex set is a number. It's a size of this set. Which set? Cut vertex set. Which cut vertex set? Whose size is minimum. In the same way, lambda is a number. Which number? It's a size of the cut edge set. Okay. So which cut edge set? Whose size is minimum. Understand? In that way, I can define K comma lambda. But in simpler words, in English, we can define K is minimum number of vertices required to disconnect the graph. Lambda is minimum number of edges required to disconnect the graph. In that way we can define that two things in a connected graph. Otherwise already graph is disconnected, then K is nothing but minimum number of vertices to be deleted to increase the connected components. Similarly lambda is nothing but minimum number of edges are required to increase the number of connected components in the graph. That's it. This is about K comma lambda. We'll see one example and we'll try to calculate K value, lambda value in this problem. Okay. Example. Let's take 1 to 2, 2 to 3, 2 to 4 like this, 5 and 6 like this. For this problem, what is K value and lambda? What is K? Minimum number of vertices required to disconnect this graph. Correct? Because it's already connected, we have to try to disconnect it. So I think if I remove single vertex, it will not be possible, right? So we need at least two vertices, right? And two are sufficient. With deletion of 2 comma 4, what happens is graph will be disconnected. 1 and 6 will be separated from 3 5. That's why minimum number is 2. With 1 I cannot do, but with 2 I can do. That means minimum number is 2. Second one, minimum number of edges required to disconnect this graph is, so can I do with single edge? Impossible. Already I told you, every edge is on cycle, then that edge cannot disconnect the graph. Then possibility is group of edges, that means multiple edges. So I think 2 is enough, right? Because what is the minimum degree of this graph? 2. Then with 2 always it is possible, with 1 it was not possible, with 2 always it is possible, then minimum number will become 2. In that way we can use minimum degree concept to decide that the minimum number of edges required to disconnect this graph is 2, right? So lambda is 2. So this is a story about edge connectivity number and vertex connectivity number. Okay. Let's discuss one problem. Let capital G be a non-empty graph. Okay, that means number of vertices are more than or equal to 1. In such conditions, statement number 1 is, if G is disconnected, then G bar is connected. True or false we have to identify. Second one, if G is already connected, then G bar is disconnected. So whenever these kind of problems are given, first of all you should understand that G represents any graph. Okay, so if you really want to say that statement 1 is correct, then we have to prove that whatever the graph is disconnected, its complement should be connected. Okay, students do these things in a wrong way like this. So some student argue like this. He will take one graph A, B, C, D and he says that, sir, see, this is a disconnected graph. Then I say yes. Then he will compute G bar. You know how to compute G bar, isn't it? So let's try it. A, B, C, D. Okay. That student knows how to compute G bar. Then he will compute like this: AC and C to B and B to D and A to D. We know how to compute G bar, right? Then he says that, see sir, G is disconnected graph, G bar is connected, hence proved. That's a wrong argument. By just taking one example of graph, and if you prove this thing, it doesn't mean that it is always correct. Isn't it so? So what can happen is, there may be some other graphs which you did not even imagine, that graphs may be disconnected because there are infinite graphs, right? So among them, few graphs may be like this. They are disconnected, but its complement also may be disconnected. Who knows? Did you check them? No. Without checking them, how can you say about that kind of graphs? So that's why finally what I want to say is, your argument is wrong. To prove that some statement is correct, it should be true for every graph. But by taking one example, you are only proving for one graph. That's why it is wrong argument. Then let's observe one more graph. Okay, but as a student, how to solve this problem I will tell you. Take one more different graph like this: A, B, C, maybe D. Okay, single vertex. Then let's try to compute G bar. Okay, then what you get? AD might be, I'm trying to calculate complement. So A to C, yes, then B to D. Then slowly I'm getting confidence that one more thing is what? D to B, D to C, yes, D to C. So I'm slowly getting confidence that S1 is correct. Okay, so that is what, but I have no proof for that. Then how to prove it? Without proving, I can't say it is correct. So now slowly try to get the proof for it. Okay, initially you tried some examples, and whatever the example you are taking, then its complement is becoming true. That means it is complement is becoming connected. Any disconnected graph you were taking, its complement was becoming connected. Then it doesn't mean that you proved for every graph, right? Be careful. Then now what should be your argument is, since your confidence is about its correct statement, then try to prove it. So how to prove, I will tell you. So that's the main goal of discrete mathematics, especially graph theory. In this graph theory, you will be learning lot of proving techniques. Okay, in entire this graph theory, I'm going to use majority of the time one common proving technique, that is proof by contradiction. Most of the time, sometimes I use some different mechanisms, try to adapt them, try to learn them. Okay, so what you do is, attend my lecture and give a thought for everything. Whenever I give some statement, apply your brain and think a lot. Okay, and follow me. At the same time, you have to apply your own brain to construct the things. Okay, first understand what I'm saying, then think in the same lines as how I'm thinking. Let's begin with that thing. If G is disconnected, any random graph G is disconnected, then why G bar is connected? That is what we have to prove that. Then let's start with G bar. Okay, in G bar, in G, since G bar is connected, right? Assume that, let's say, really G bar is disconnected. Okay, and G is also disconnected. Then definitely statement 1 is false, isn't it? Because the statement says that whenever G is disconnected, G bar is disconnected. Let's take G is disconnected, G bar is disconnected. If it is possible, then only S1 statement is wrong, right? Understand my point? The claim of the statement is whenever G is disconnected, G bar should be connected. Let's say that claim is really wrong. That is called proof by contradiction. Then G bar should be disconnected, G also should be disconnected. Really such graph exists, let's say that is G. Then we'll focus here. G bar is disconnected. Then I ask one thing. Which kind of graphs are disconnected generally? When graph has minimum one vertex. Already I told you, whenever a graph is disconnected, then there is no path between at least two vertices, because between every two vertices there is a path, then that graph is connected. Then definitely you should see at least two vertices like Raju comma, let's imagine them as real world characters like Raju comma Rani. What's the property of Raju and Rani? Let's say Raju and Rani are two vertices which doesn't have any path. If Raju and Rani, even Raju Rani has a connection or path, then G bar cannot be disconnected, isn't it? Whenever G bar is disconnected, there exist at least two vertices Raju comma Rani. So they should not have a path. There is no path between them. You understand this point? Let's say really it's possible. Let's say then same Raju Rani should be part of G also, right? Let's represent Raju Rani here too. Okay, so this is Raju and Rani. I don't know whether they are connected or not here, because G is disconnected. Then this Raju Rani may be connected, may not be disconnected. Don't say that Raju Rani are disconnected. Then I ask why. Then you say, sir, it is disconnected graph. In disconnected graph, some two vertices are not connected. It doesn't mean that they are Raju comma Rani, right? So that's why. But I know that in G bar, Raju and Rani are disconnected. That is what is the starting point. But same Raju Rani may not be disconnected here. They may be connected, may not be connected. Maybe some other two vertices are disconnected. That's the reason this graph G is disconnected, not because of the reason Raju Rani. But my assumption is Raju and Rani are the main reason for this graph's, let's say, disconnection. Whose disconnection? G bar. I don't know about Raju comma Rani in G. Whether they are connected or disconnected. Okay, let's start with this point. Then I prove that whenever Raju comma Rani are disconnected, so what happens? Let's go to G. Okay, so let's go to G. In that Raju Rani, case number 1. In case number 1, this Raju Rani may be connected. Second one, case number 2, where Raju comma Rani are disconnected. Okay, so let me show case number 1 as connected. Case number 2 is what? Raju Rani disconnected. First assume that case number 1, Raju Rani are connected. If Raju comma Rani are connected but graph is disconnected, now stop the video and think. Raju Rani are connected but overall graph is disconnected, then definitely there will be one more connected component, isn't it? Otherwise, if there is no another component, then there is only one component, graph will be connected. So that's why I can see one more component in this graph. Then let's say that component will have at least one vertex. Let's call that vertex as Rakesh. Understand my point? Sir, what if Rakesh doesn't exist? Then no vertex exists in this component. Then every component should have at least one vertex, otherwise it is not component. Then no component will be there. Then you will have only one component. But we know that in disconnected graph there exist at least two components. Sir, null graph will have zero components. See the assumption. Number of vertices are greater than or equal to 1. Then there is no null graph. Then all other graphs will have definitely at least two components. Let's say this is component number 1. Then there is another component, let's say, that is this one. In that Rakesh is one vertex. Then I would like to ask some questions about relation between Raju comma Rakesh. Since Raju Rakesh belongs to different partitions, then since Rakesh is part of G, he also should part of G bar, because G and G bar are designed on same vertex set. Then my question is, here Raju Rakesh are not connected directly or indirectly, then definitely there should be direct edge between Raju Rakesh. That's a property of G bar. Whenever there is no edge in G, definitely there will be edge in G bar. Similarly, since Rani Rakesh are not directly connected, and definitely there will be a direct edge between them. Initially your assumption was Raju Rani doesn't have path, but I can prove that there is a path. Remember, right? Initially you assumed that Raju Rani doesn't have path, but I proved that there is a path. In which case, when Raju Rani are connected here. Let's take the second case. What is the second case possible for this Raju Rani? The second case for Raju Rani is Raju Rani belongs to different partitions. What if Raju Rani belongs to different partitions here? Let's say Raju belongs to one partition, Rani belongs to one partition. Then it's very easy. Since there is no edge between them directly, that's the concept of two different partitions. Then directly Raju Rani will share an edge. Hence Raju and Rani are again connected. Now see, whatever the case you take, now let's summarize the concept. Whenever G bar is disconnected, always you should prove that there are two vertices, Raju comma Rani, correct or not? And there is no path between them. Whenever there is no path, then I will go to G, then I will see two cases. One is if Raju Rani are two vertices, maybe they are directly connected. If they are directly connected, already I proved that here also they are connected through Rakesh. If they are not directly connected, then again I proved that Raju and Rani are directly connected. So that's the story. Finally, what it says, whatever may be the reason, Raju Rani, that means Raju Rani should be connected. But if graph is disconnected, definitely there should be two vertices which are not connected, but you are not able to show them. Why? Whenever you show them, I am proving that they are connected. That means what? You are the loser. That means always you lose the game if you assume G bar is disconnected. That means whenever graph is disconnected, G bar cannot be disconnected. Whenever G bar is disconnected, you should show two vertices Raju Rani. Whenever you show two vertices Raju Rani which are disconnected, then I will go to G and I will come back and I prove that Raju Rani are connected using two cases. And if you don't understand it, don't worry, again see this video, you will definitely understand it. But whenever you don't understand a point, stop the video and start thinking. So this entire graph theory is about improving your thought process. So that's why keep learning and keep thinking. Okay, let's see second statement. If a graph is connected, then G bar is disconnected. Really this statement is correct, then it should be true for any graph. Okay, so what I do is I take one example graph with very less number of edges, but I connect it somehow. Example this one. Okay, yes, this is a graph G and this is connected. To connect it, I have taken as less number of edges as possible, and I would like to observe G bar. Is this G bar is connected or disconnected? I want to observe. Let me do it. 1, 2, 4, 3, 5. Okay, so between 1, 3 there is an edge. Between 2, 4 there is an edge. Between 5, 3 there is an edge. Right? Between 1 and 4 there is no edge here, means definitely there is an edge. Already see it's connected, and few more edges I supposed to add to this one, right? So what I want to say is this graph G is connected, its complement also connected, but the statement says that whenever a graph is connected, its complement is disconnected. That is false. The reason, we have an example. Understand? So finally, this is not always true. Whenever some statement is not always true, that means it's false, right? Let's see one more question which is asked in GATE 2003 paper. Let's read it. There is a graph G which is a random graph with n nodes and k components. Okay, that means you have n nodes. Node means vertex, like there are n vertices, and k components. Example, this one, 1, 2, 3, like this, and 4, 5, 6. This is a graph with 6 nodes and 2 components, like k value here 2 and n value 6. I'm just understanding the problem. If a vertex is removed from this graph G, then the number of components in the resultant graph. So what happens to the number of components? Okay, so the range is given. it must necessarily lie between. Okay, he's asking, so what's the range of values possible for the number of components in the resultant graph? Example for this graph we'll see. If I remove vertex 3, what happens? The number of components will become, so initially it was 2, now again it is 2, right? So whenever number of components are 2, now again it become 2, but it may increase, it may decrease. So all these possibilities we have to think. So how I solve this question, you see, I'll directly go to options, and the number of connected components cannot be n at any time. Why? Since you are removing one vertex, initially you have n vertices, right? I don't know the structure of your graph, whatever the structure it will be. Okay, then any graph cannot have more than n components, isn't it? When you have n vertices, you can have n components, where every single vertex is a component. This is the only case where you will see n components like this, right? So now if you remove one vertex from that, then the number of components will be decreased by definitely by 1, then it will become n minus 1, because you are losing one vertex. Then the remaining vertices are only n minus 1 in the graph. Then how can you have more than n minus 1 components? Impossible, because every component should have at least one vertex. Then maximum components you can have is n minus 1. Then you never have n components in the resultant graph. That's why option A is wrong. See this one, k minus 1 and k plus 1. Why the number of components should be just one more than the previous number of components? Why not, if I remove some vertex, sometimes what can happen is number of components will be drastically increased. I will show one example. Example, star graph. You see this star graph, 1 2 3 4 5, like this, 6 7 8 9. Number of components here is only 1, k equal to 1. In this case, if I remove single vertex 1 here, what happens? Then all these edges will be removed, isn't it? So if I do that, then the number of connected components in the resultant graph is, see, 1 2 3 4 5 6 7 8. K value 1 become 8. That means what? So whenever you remove a vertex from the graph, in the resultant graph, the number of connected components might increase by more than 1 sometimes. That means k plus 1 is upper bound is wrong, right? So absolutely option B wrong. It may be more than 1 also. So now we'll see the option C, option D. K plus 1 and n minus k. It is very simple. Whenever you have k components, this range says that number of components will become k plus 1 to n minus k. Sometimes number of components remain same. Example, if that vertex is not cut vertex. Okay, let's take one vertex which is not cut vertex, like this. In this graph, number of components are 1. If you remove any vertex, example, if you remove 1, then still number of components will become 1. But this option says that the range will be from k plus 1 to n minus k. This indicates that always there is an increment in the components. Absolutely wrong, isn't it? Option D is gone. Then option C is the only choice. So maximum number of components you get n minus 1. The case is where you have k components, but when you remove the one vertex, probably every vertex becomes a component. Example of such graph is star vertex. Like if your vertices are connected like this, all vertices are like 1 2 3 so on n. Okay, n minus 1, this nth vertex. If you remove this one single vertex, center vertex, then the number of components will reach suddenly n minus 1. That is the upper bound. Lower bound is, so k plus 1 and n minus 1. So there is a mistake actually. This was k minus 1. Okay, let me add k minus 1 here. So let me correct here. It's k minus 1. So definitely k minus 1 also possible. Whenever you remove a vertex, why connected component will be decreased? I will tell you one scenario. That scenario is like this. Example, you have a single vertex and component like this. Okay, in this case, number of connected components, let's say k. When you remove this isolated vertex, then what happens? then one component will be gone. Then this overall k components, example component 1, component 2, component 3, component 4, let's say, and fifth component is dot, like the single vertex. If I remove it, then the number of components may be decreased by only one. So that's why k minus 1 is the minimum value and maximum value is n minus 1. That's why option C is correct and it is k minus 1 and n minus 1. Okay. Let's see one more problem. If u is a cut vertex, then graph minus that cut vertex whole bar. You know what is this minus operation, right? You know it's a vertex removal. After removing a vertex, if you apply complement, such graph is connected. Yes or no? We'll see. So we'll try to understand this problem first. So for that we need a cut vertex. Okay. Before going to examples, let me fix one example like this. This is a graph with single vertex. Okay, it is connected, isn't it? Okay. Second one, if I remove this vertex from the graph, what happens? You end up with null graph. Okay. Already I told you null graph is not a valid graph. Okay. So that means if I remove this vertex, then what is the definition of cut vertex? Whose removal either disconnects the connected graph or increases the number of connected components. Nothing is happening because when you remove it, you are ending up with null graph. So null graph is not a graph to discuss whether it is connected or not. Second one, whether we are increasing the connected components. That's why. So single vertex is not a cut vertex. Question is about if a graph contains a cut vertex, then something else, right? So that's why what I do is I take a graph with at least one cut vertex. Let's take like this. I'm just understanding what is it, this statement 1 2 3. So here we know that 2 is a cut vertex, isn't it? So question is, if I remove 2, this is your graph G, then operation we have to do is G minus 2 whole bar. Let's do it. 1, I'm removing 2 first, then you end up with 1 comma 3. Okay, this is your G minus 2, but I want this is G minus 2. And what is G minus 2 whole bar? G minus 2 whole bar is nothing but complement of 1 3. Then since there is no edge between 1 3, now we have to add in complement. We know what is complement. So finally you end up with connected graph. It doesn't mean that I am saying this is always correct, but we have taken one example and we have validated it. But I'm not saying that it is always true. I don't know. That is what we have to prove. Okay. Without proof, I can't say that. But I'm just understanding the problem. Let's take one more example to understand this problem clearly. Let's take a triangle 1 2 3 and one more triangle like this. Okay, 4 5 6. Let's say there are two cut vertices. One is 2, one is 4. Okay. Now let's try to check with respect to 2. G minus 2 whole bar. What happens to that? So let me draw first G minus 2. Then you end up with 1 3 and 4 5 6, isn't it? Then I remove 2. Now it's complement. We have to apply complement of this graph. Then what happens? 1 3 4 5 6 are the vertices. Whenever there is no edge between any two vertices, now we have to add. Then 1 4 1 5, so 3 5, so 3 6, so many, right? So finally graph is connected. Maybe I don't know, like I'm not adding all the edges, but graph is already connected. So that is what this theorem says, right? G minus U whole bar is connected. But is it always true? I don't know, because I have taken only two examples. But that two example doesn't prove the statement. So what to do then? Then I try to cover all the cases by taking a random graph. Let me take a random graph G. I don't assume any structure, and if I prove anything for this graph, then it is true for everything. And let's say this graph has a cut vertex. Okay, this is your graph G and there is a cut vertex U. What's the property of cut vertex? If you remove it, graph will be disconnected, or otherwise number of connected components will be increased. Correct? So let's take two cases. Case number 1, where graph is, let's say, already connected. Your G is, graph G is connected. Second case will take where graph is disconnected. Okay. In first case, when graph is connected, then if vertex u is cut vertex, what happens? If you remove it, graph will be definitely disconnected, because when there is only one component, what's the property of cut vertex? It increases the number of connected components. So if it increases the connected components, then already graph is connected, there is only one component. If it increases, then it will become 2 or 3 or so on. So what I want to say is, your resultant graph after removal of vertex u is disconnected graph. So that you should remember. So finally we are getting disconnected graph, right, after removal of u. Agree? Then its complement. Whenever you do complement, please remember the result. Already in previous lecture or previous session I taught you that any disconnected graph's complement is connected. So here you have a disconnected graph. We are applying complement to that one. So disconnected graph's complement is connected. I proved that your graph is connected when your G is connected. Whenever G is connected, G minus U will become disconnected. Disconnected bar is disconnected. Second one. If already graph is disconnected, then you have some connected components. Whenever you have a disconnected graph, you will have at least two components. Yes or no? If graph is connected, you will see one component. If graph is disconnected, you will see multiple components, more than two, more than one, maybe two, maybe three. Let's say this is your graph with some components. Then when already your graph is disconnected, what's the property of cut vertex? It increases the number of connected components. Let me remove U from it. If I remove it, then the number of connected components will be increased. So that means graph will be more disconnected. End of the day, so G minus U also disconnected. Why? When connected components are increased, then definitely graph should be disconnected, because connected graph contains only one connected component. Okay. So when connected components are increased, graph is disconnected, and when graph is disconnected, then you are applying what? After G minus U, bar. That means we are computing such disconnected graphs complement. So disconnected graphs complement is connected. So already we proved it, right? So using this only one concept, that any disconnected graphs complement is connected. Using that we are proving that G minus U whole bar is always connected. Okay.